In the first image, you're looking at the overall EDI system, the final purification layer before hydrogen production begins. Water enters this system after reverse osmosis treatment, but even after RO, tiny dissolved ions still remain inside the water. These remaining ions may be microscopic, but inside PEM electrolyzers they become dangerous over time. The EDI system removes those final traces using a combination of ion exchange membranes, electric fields, and continuous purification. On the left side, RO permeate enters the system. In the center, the EDI modules begin electrically removing ions. And on the right side, ultra-pure water exits toward the EPM electrolyzer. This is one of the hidden realities of hydrogen infrastructure. Before electricity can split water into hydrogen, another electrical system is already purifying the water itself. The second image reveals why reverse osmosis alone is not sufficient. Even after molecular separation inside RO membranes, trace ions still remain dissolved in the water. Conductivity may already be low, but for PEM electrolysis, low is not enough. Residual sodium, silica, carbon dioxide, chloride, calcium, magnesium, and dissolved ionic species can still damage sensitive electrochemical systems over time. This image shows the hidden threat of conductivity. Tiny remaining ions increase electrical resistance, contribute to contamination, accelerate membrane degradation, and reduce long-term reliability inside the electrolyzer stack. This is why industrial hydrogen systems require a final polishing layer beyond RO. The electrolyzer demands water approaching ultra-pure conditions. Now in the third image, we move inside the EDI module itself. This is where purification becomes electrochemistry. The system contains alternating ion exchange membranes and ion exchange resins arranged inside electrically active compartments. As water flows through the module, a direct current electric field is applied across the system. Positively charged ions migrate toward the cathode. Negatively charged ions migrate toward the anode. Ion exchange membranes selectively allow specific ions to pass while blocking others. The resins capture and transfer ions continuously. Unlike traditional mixed bed ion exchange systems that require periodic chemical regeneration, EDI continuously regenerates itself using electricity. This is one of the most elegant hidden systems inside industrial water purification. Electricity is being used to prepare water for another electricity-driven process, electrolysis. The fourth image focuses on electrically driven purification. This is the core operating principle behind EDI technology. Direct current power creates an electric field across the purification stack, and that electric field becomes the driving force behind ion migration. Contaminants are continuously removed from the water stream without large chemical regeneration cycles. This creates a more stable, lower maintenance purification process capable of delivering extremely low conductivity water continuously. The glowing blue channels represent ultra-pure water formation inside the stack, while the directional ion movement visualizes cations and anions migrating out of the product stream. This image matters because it shows that water purification itself becomes an active electrical process rather than passive filtration alone. In the fifth image, we see the result: ultra-low conductivity water. Conductivity is one of the most important hidden metrics inside hydrogen water systems because conductivity directly reflects the presence of dissolved ions. Raw water may begin with conductivity levels measured in hundreds of microsiemens per centimeter. Reverse osmosis dramatically reduces that conductivity, but EDI pushes conductivity even lower, approaching ultra-pure levels below 0.1 microsiemens per centimeter. This image visualizes the final purity transformation. The water leaving the EDI system is now suitable for high-performance PM electrolysis. And this matters because electrolyzer reliability depends heavily on ion-free water conditions. The cleaner the water, the lower the contamination risk, the lower the scaling risk, and the longer the stack can survive under continuous industrial operation. But even EDI systems face hidden operational stresses. In the sixth image, we see the complete purity chain operating together: reverse osmosis, EDI purification, ultra-pure storage, and PEM electrolysis. What this image really shows is systems integration. The purification system is no longer a standalone water treatment process. It has become part of the electrochemical infrastructure itself. Every stage depends on the previous stage surviving properly. If RO performance declines, EDI performance suffers. If EDI performance suffers, electrolyzer stability declines. This interconnected dependency is one of the most important realities in industrial hydrogen systems. The visible electrolyzer is only as reliable as the invisible infrastructure supporting it upstream. The seventh image moves deeper into performance and protection. Here we see EDI operating as a continuous purification engine, feeding the electrolyzer with stable, ultra-pure water. The electric field continuously removes ions while protecting downstream PEM membranes, catalysts, and electrochemical surfaces from contamination. This image highlights one of the biggest hidden engineering truths in green hydrogen. Ultra-pure water is not optional. It is foundational. Poor water quality quietly increases degradation, maintenance costs, stack resistance, contamination risk, and operational instability. High-purity water, on the other hand, allows the electrolyzer to operate closer to its intended performance envelope for much longer periods of time. And finally, in the eighth image, the entire purification philosophy comes together. The complete chain begins with reverse osmosis, removing the bulk of dissolved contaminants. EDI then removes the remaining ionic traces through electrically driven purification. Ultra-pure water is stored and delivered to the EPEM electrolyzer. And finally, hydrogen exits the system. This final image reveals the hidden industrial ecosystem behind green hydrogen. Most people focus on electrolyzer capacity, hydrogen production targets, or renewable electricity inputs. But underneath those headlines is an invisible infrastructure dedicated entirely to water purity, ion control, membrane protection, conductivity management, and long-term electrochemical reliability. Because the future hydrogen economy will not be built only by bigger electrolyzers. It will be built by the hidden industrial systems that allow those electrolyzers to survive under real operating conditions. And EDI is one of those hidden systems. It is the final electrical purification layer before hydrogen production begins. If you want deeper breakdowns of electrolyzers, ultra-pure water systems, hydrogen infrastructure, industrial decarbonization, and the hidden engineering systems powering the future energy economy, explore H2 Hub by Renee Energy using the link in the description.